Hello, my name is Kenny Longa, and today we're going to be using VPython to model the solar system. And in this, one of the major questions we'll try to grasp is can we predict the length of a day, month, and year using VPython? Topics covered will include components, momentum, and several other factors. Using VPython and a little help from the internet, we were able to almost create a complete replica of our solar system. One, starting off with the gravitational constants we were given in class, 6.7 times 10 to the negative 11, and the masses of each of the planets, ranging from Mercury to Neptune. Also, with a little help of the link given on T-square, we were able to find the orbital velocities of each of the planets. And we were able to, using the mass we have from each planet and multiplying it by the orbital speed, the initial momentum of each planet. Now, what we needed to do is perfect the rotation of the planet. Now we use the while loop, and after that, we needed to find the final momentum, which is always given P final equals P initial plus F net delta T. We needed F net. Now, using information gathered, we were able to find F net by multiplying it by the equation always given. Gravitational constant times the mass it's being rotating around, times the mass of the planet in this case, divided by the magnitude of the radius, which you calculated here. Once we've given that, our task was quite simple. We were able to find the final position, and in addition, we were able to find the final momentum, and we completed this process for each of the planets. Now what we're going to do is we're going to run so we can get a glimpse of our solar system. And as you can see, we have a planet rotating around, and it's almost a complete replica of our solar system. And if one wanted to zoom out, you can see even more planets. Now that we've found and completely modeled our solar system, the questions that were mainly asked were, can we find the length of the year, month, and day? Now, using a couple of properties we learned in class, we found that to find the time period of one revolution, or in this case for us, a year, is 2 pi r over velocity. So, having calculated the velocity originally in codes prior, we can find the total time period it takes for the Earth to rotate in seconds of a year. So, first, for the first part, as seen here by the code, using 2 pi r, 2 pi times the radius of the Earth, which we found here, using this. So using code we've obtained prior, we can calculate the total time period it would take for the Earth to travel around the entire orbit would be 2 pi times the radius of the Earth divided by the final velocity of the Earth. Now, knowing this, we'll get an answer about in some amount of seconds, very similar to the one we have here. Now, with that, knowing this, we know that in a year there are 12 months. So to simply find that, we can just divide the answer we got originally by the number 12. That will give us another answer in seconds. Now, knowing this, the average amount of days in a month is about 30.6. For in this case, we're going to put 30, since there's more months with 30 than 31. Knowing this, we'll just divide that answer by 30. Now, by this process, we can critically and almost find the exact amount of seconds there are in a day, month, or year. But we can only do this with prior knowledge that there's 12 months in a year and 30 days in a month, thus solving our problem. In conclusion, with a little help of VPython and an interesting lab topic, we're able to model our solar system using VPython and calculate things such as year, month, and day, kind of putting into perspective how we're able to obtain certain data that we have now, thus concluding another interesting project. Thank you for watching. Good evening.